Welcome back to my channel Shri Statistics. So today we are going to find the eigenvalues and eigenvectors and the singular value decomposition for a matrix A. So we know that from the definition the singular value decomposition can be written in this form. And I have also mentioned in my earlier videos as to how you can calculate the number of rows and columns here. So first we find A transpose A. So supposing this is equal to B, then the characteristic equation of B is B minus lambda I. So we subtract lambda from this. So this will give us an equation. When we solve this determinant, then we come out with an equation, and from this, on solving this equation, we are able to find these values lambda as 0, 1 and 2. So these are the eigenvalues of this matrix B. Now supposing we consider the system, that is this B into x, y and z would be equal to 0. So for each particular lambda we calculate the corresponding eigenvector. So we put lambda equal to 2, say, in the first one. So then we just substitute 2 over here, and on solving and on using some elementary row functions, that is, we take the second row to be equal to the sum of the second and the first row. So on solving this equation, you can see that we get z is equal to 0 and minus x plus y is equal to 0, which implies x is equal to y. So putting y is equal to k. Why are we putting y equal to k? Because here, from here, then we can find x is also equal to k. So again we substitute it in these equations, and here then we come out with this value, that is 1, 1 and 0, which is an eigenvector of B corresponding to the eigenvalue lambda equal to 2. Similarly, for lambda equal to 1, putting it again in that system of equations, and again we have here, this time we are interchanging row 1 and row 2. Why are all these things being done? This is just for ease of calculation. So over here it can be seen that there is only this if z is equal to k, then again we are able to take out k from here, so that will leave 0, 0, 1. So here we are again finding this as the required eigenvector. Similarly, for lambda equal to 0, it is solved in the same way as it was for the previous two eigenvectors. So here you can find that the final eigenvector corresponding to lambda equal to 0 is minus 1, 1 and 0. Therefore, these are the eigenvectors which are obtained. Now, to normalize these eigenvectors, if you would recall that you have to divide by this square root. So according to that method, if we find out, if you recall from my past video that we were taking the descending order of these values, and so here after on solving this, it comes out to be this v. What is this v? This v is over here, this v. So after solving this, we can calculate this sigma u and v, and therefore it can also be verified that this satisfies the condition for the singular value decomposition. So basically this is a solved example. It is rather lengthy, but this is how this is the actual use of singular value decomposition theorem. So that's all from me for today. Thank you for watching.